Hi everybody. We're going to start on section 6.1. We'll jump right in. We're transitioning from discrete variables to continuous variables. Just a reminder, a discrete variable has values that are separated, and you can list consecutive values, so you can say 1, 2, 3, 4 like that. If those are the values of a variable, then the variable is discrete. Continuous variables can't be listed like that. You can say a person is 6 feet tall, or 7. Of course, that would be really tall. But any value between those is also possible. So 6.1 and 6.01, there isn't actually a way to list the possible values, because any two values you list, there's always something you will have missed between them. So there isn't really such an idea as consecutive values when you talk about continuous variables. And if you can't list all the values, then you can't associate probabilities by just listing them. So we need a different tool for continuous random variables when it comes to relating values to probabilities. And just a reminder, when you associate values of a variable to probabilities, that's called a probability distribution. And the goal right now is to come up with a probability distribution that works for a continuous variable. So here we are in lesson 6.1. I'm just going to go ahead and read. So in this lesson, we begin the study of continuous probability distributions used to describe the distribution of continuous random variables. The histogram below gives relative frequencies for a huge random sample of men's heights, a population whose mean is assumed to be 69 inches. That's a kind of a rough rounding of the average height of men. Each bar has a width of 2 in the histogram, and the height is scaled so that the area of the bar is equal to the probability it represents. So you get one of these distributions that's sort of bell-shaped, but it's a histogram, and the widths of the bars are sort of arbitrary. The bar widths could have been any value, and let's just go ahead and start answering some of these questions. So as I mentioned, men's heights are a continuous variable. In this diagram, or in this histogram up above, the class width is 2. So one of the bars here goes from 70 to 72. So that's a width of 2. We can make the class widths smaller, like this one. If you look real closely, the class width is 0.5 because there's 2 bars per inch here. So what's the class width now? 0.5. Okay, and the histogram looks more like kind of just a bell with smooth edges, but it's not smooth yet. Here I redid the diagram, and now there's about 100 bars. The area of each bar represents a probability. What's the total area of all the bars? Well, the total area has to be the total probability, and we've said that the total probability is always 1. So let's go ahead and make that. The sum of the probabilities and the probabilities always add up to 1. Now below, I've got with 100 bars, you can just kind of see that it starts to make sense to use a smooth curve to represent the distribution of probability. This time the smooth curve right here is called a probability density function. The bell-shaped curve that you're looking at here is symmetric, and it's referred to as the normal distribution because it's one of the most common distributions of probability. It's also referred to as the Gaussian distribution, and that's named after the guy who didn't really invent it first. He claimed he invented it first, but we think it was invented by another guy, which I'll mention in a second. Okay, I already mentioned that the probability curve is known as a probability density function.
Thanks, Andrea. Okay, so the normal probability distribution, which is the one that we're looking at, that's a normal distribution. It asks for the formula here. I'm going to give you the formula, but we'll never use it, so don't panic. Okay, so it's y equals e to the negative 1/2 times x minus mu over sigma. Squared over sigma times the square root of 2 pi. That's the Gaussian distribution. And if you graph it, it makes the bell curve up above. You need to know the mean, which is mu, and the standard deviation, which is sigma. I guess I could put that in here. So mu is the mean for the population, and sigma is the standard deviation for the population. Okay. Distribution was discovered by, I mentioned his name, it was Abraham Demave, but it's French, so it's a, I don't even know if it gets that accent. We just say Demave, and so it's some strange pronunciation. Why is it so important? It's funny, but it's hard to explain. But, I mean, you would first say that many distributions of data are normal. I will say approximately normal. I'll say normal in distribution. I don't need to say any, that's redundant. But let's say including sample means and sample proportions. And I'll say, I don't have any, so I'll get to the details later. So we spent a lot of time studying sample means. And the rule is basically, as long as your sample size is bigger than 30, we can pretty much guarantee that sample means will have normal distribution. And same thing with the proportions. If you get your sample size large enough, it's a slightly different rule for the proportions. But if you get your sample size large enough, proportions will also have bell-shaped distribution, a normal distribution, and that right there is enough to justify the existence of the distribution. Now, next it says in the following lessons, we're going to learn to find areas under the normal probability density function. Again, the curve is a density function. And the areas under the curve will be probabilities. Now, it's asking for a specific distribution here. This one's called a uniform distribution. We've talked about that word before. Okay. The uniform distribution, uniform just means the same, right? So it's the same everywhere, which means that it's flat. All the height is the same everywhere. Total area under the distribution is always 1. The range for this variable, well, the min is A, and the max is B, and so range is always max minus min. So that'll be B minus A. Okay, the density function is the height of the rectangle. Y equals what? Is the equation for that curve on top. Remember, the height is y. The width is the range. Area, oops, the area is the probability. Area is width times height. That has to be 1. And if width times height is 1, then these are reciprocals of each other. The only way two numbers multiply to give 1 is if they are reciprocals. So the height has to be the reciprocal of the width, which is going to be 1 over B minus A. Okay. Okay, and so the density function, I'll put up here as well, y equals 1 over B minus A. So the total area will be 1. Okay, what does the area represent? This shaded, that's a probability. Areas are always probability. This would be the probability that the randomly selected value x is between C and D. So C less than or equal to x less than or equal to D is how we'll represent that. That's just the shaded area. Any questions? Okay. I have a silly little problem down here, and this is just kind of help us get a sense of how you could use a uniform distribution. I'll never put this on a test, but I consider it sort of important just because uniform distributions are easy, and it gives us a sense of the concepts. So here's the problem. It says a children's day camp enrolls children from 5 years of age up to their 10th birthday. If a child is randomly selected, age is a continuous variable that ranges from 5 to 10 with probabilities distributed uniformly. It just means that they've got kids of all ages with equal probability. Okay? So the question is, what's the probability density function? Well, in the range, you can see is the width, and that's going to be 10 minus 5. So the range is 5. And so the height has to be 1 over the range, so that the base times height is 1. So the height is just going to be 1/5. So on top we say y equals 1/5, and that's what we call the density function, the curve that makes the top of the probability distribution. Y equals 1/5. Okay, looking for questions, and I don't see any. Okay. Now, they ask what's the probability that a random child is between 6.5 and 9.5. And it says to shade it and give the probability. So 6.5 to 9.5. Okay, and so we already know the height of this rectangle, and that's, you know, these are rectangles, so this is super easy. The height is 1/5, which on a calculator that's just 0.2, and then the width goes from 6.5 to 9.5, so you just do 9.5 minus 6.5, and I think you'll get 3. And that's really all we need to worry about. The probability that the random variable is between 6.5 and 9.5 is just base times height. So the base is 3, the height is 0.2, so this looks like is going to be 0.6, which you would write as 60%. Okay, and that's just, 60% of that rectangle is shaded. So that's the probability, 60%. Okay, I'm going to pause for questions. Okay, continuing on. This is a strange distribution shape, but it again is a probability curve. And what I did was I imagined 2 populations of fish. One is a light fish, the other a small fish, the other is a larger fish, and in other versions of this activity, I've had the small fish be called a bream, and the larger fish is bass. And the bream is a pretty small fish compared to a bass. And when you mix 2 populations together, you can get a distribution of probability that has 2 modes. So you're going to have a mode there for the smaller fish, and another one there. That's for the bass, the larger fish. And this is a data set that we call bimodal. Okay, so the distribution has 2 peaks. Okay, and that, again, that happens when you mix 2 populations together sometimes. If they're different, they're different. Okay, now it says the mean of the fish of the weights of the fish is 1.7 pounds. So these are weights on this distribution. Random variable is continuous. That's a weight. You can't count that. So it's continuous. So we can compute the probability for any range of values. Any range, but what I did was I sliced it up. And in calculus, I actually figured out the equation for that curve there just by working hard and dreaming up an equation. And once I had the equation, I need to make sure that the total area is 1. So you just divide the equation by its area, and then you end up with this probability curve. And then I use calculus to slice this thing up and find the areas under all of these bits that I'm showing here. So you wouldn't know, would be expected to do anything like this. But I just want you guys to just kind of see how the areas line up like this in a probability curve. Okay, so it says note the distribution starts at 0 because you can't have a fish with anything below 0 in weight. And the probability curve goes on, but it basically zeroes out at about 5 or 6 pounds because there just aren't many fish in the lake that are that heavy. And if any at all. What's the total area under the curve? Okay, you don't need to compute this. What's the total area? If you add those up, what we get? 1. Thank you, Nicholas. Okay, now the probability that x is between 1.5 and 3.0. So I'm going to shade that. And remember, the probability is the area. I don't know if you guys want to shade this because we're going to have several questions on this. And you're going to want to keep referring to it. It's easy for me to erase, but harder for you maybe. Okay, so there's that's my area. I would add those areas up. 0.26 plus 0.18 plus 0.09. Does anybody work that out? Let's see. 44, 44. That's what I got, 2.53. And so 53% of the fish in the lake are in that weight range. So it's a probability of 53%. Now, if you want to know the probability that a fish is exactly equal to 1.5 pounds, I'm representing it geometrically here. That red line is exactly at 1.5 pounds. What's the probability that a fish is exactly 1.5 pounds? Or exactly 3 pounds? Well, 1.5 is a measurement that has no thickness. That line has no thickness. Lines don't have area because they have no width. So if you include that line, the area is 0.53 as we computed. If I erase the lines, it's still the same area because those lines don't make it thicker. So the area is still 0.53. And I'll just do it this way. Probability 1.5 less than x less than 3.0, which is 0.53. So the region is not smaller. So the probability does not change. So the question below is, does it matter if we include endpoints on intervals when working with probabilities for continuous variables? So up above, we included 1.5 and 3.0. Then we excluded the endpoints. We get the same answer because the region is the same width either way, whether or not you have those endpoints there. Okay? So no, it does not matter if we include endpoints. What's the probability if we of randomly selecting a fish that weighs exactly 2 pounds? The fact is, there's probably no fish in the lake that's exactly 2 pounds. And you can see what I mean is 2.000, infinite number of zeros. Exactly 2 pounds is this fish right here that I'm drawing, a line with no width. Therefore, no area, therefore, no probability. So the probability is 0 for that. Okay, any questions about that? I'm going to pause for just 1 second. I got to get something.
Black leather glove, no sequin. Buckles on the jacket, it's elite shit. Nike crossbody got a piece in it. Don't you wanna dance?